Hello and welcome to Unit 6, Lecture A, Basics on the Periodic Table. Brief history of the development of the periodic table in the first place. Scientists like to classify everything. It makes it easier to look for patterns and to make generalizations, so they wanted to classify the elements as well, and they looked for general patterns. So the first kind of attempts at classifying them put them into groups of three. Now remember, they didn't know all of the elements that we know now. So things like the coinage metals, copper, silver, and gold, which you could just mine straight from the ground and were all highly malleable and shiny pretty colors, were one triad. There are only three metals that are magnetic: iron, cobalt, and nickel. So those got put together into a triad. They had limited numbers of gases. The gases all got put into a triad. When equipment got better and they could find more elements, that didn't work anymore. Next attempt, they noticed that there was this repeating pattern. Every eighth element showed the same kinds of properties. And if you look at our modern table, you're talking about things like group 1, 2, and 13 through 17. Noble gases were harder to isolate. So every eighth element, so you had 1 through 7, and then on the eighth element it repeated the same pattern. Those groups, 1, 2, and then 13 through 17, made kind of a squarish table that they were going for, and they called it the law of octaves. So you had this repeating pattern of every eighth element. They found more elements, so the law of octaves didn't work anymore, and they were still looking for something else. So the one that they really kind of want you to know is Dmitri Mendeleev. Right here are some of his hand-sketched notes where he was putting things in tables. He put the information that he knew for different elements on cards. These are the elements that they knew at the time. And he started arranging the cards in rows that we call periods now, horizontal rows, and vertical columns that we call groups now. And he started putting them together, and he put them in order of mass. So you can see he left big gaps here. He doesn't have the noble gases here. There's no helium. And they're in order according to atomic mass. And things that he wasn't sure about, he saw too big of a gap from 40 to 56, and these calcium and strontium acted the same, but he didn't have anything that acted like cesium here. So he left a gap. He put a question mark. And you'll see here and there he did that throughout his table, things that they weren't quite sure of the masses of, he put question marks next to, etc. And that was his first development. So he said that scientists, of course, are going to build on other people's work, so he acknowledged that he used other people's works. Here's kind of one of his working tables. And you'll notice that he has hydrogen in two places, because sometimes hydrogen acts like a group 1 element where he's making positive ions, and sometimes he acts like a group 17 element where he's making negative ions. So he actually has hydrogen in two places. The noble gases are lined up. What we have as the transition metals are the ones in blue here. Instead of stretching the table out, they're just in a different color. These are the guys that are jammed in the middle. But he still has all of the noble gases lined up. Those are the orange guys. The halogens are all lined up. There's oxygen's group. So pretty much exactly the same as our table. We do one thing different, and that's that we realized once we could count the number of protons in the nucleus, it's the number of protons in the nucleus that identifies the element. So our table is arranged in order of atomic number. Our table is arranged in order of increasing atomic number. That's the number of protons. It's the most important number, and we have a periodic pattern. So elements are a periodic function of the number of protons in their nucleus, and that's the way the state will say it or phrase it on your final exam. Horizontal rows are the periods, so horizontal goes from side to side, and we're going to see properties that show the same general trend. Sometimes they can go up and down a little, so as you're going, say, up, it might like dip down and then go up again, something like that. But we're looking for the general trend, not element by element trend. So horizontal rows are the periods. They are numbered going down the side. The period number tells you the number of principal energy levels. So on our periodic table, here is labeled periods. Period 1, really short, only hydrogen, helium. Period 2 and 3 are going to be great example periods because they only have the characteristic elements. They're going to show the trend really well. The transition metals aren't in there. These guys, 3 through 12, are called the transition metals. And we'll talk more about specific groups on the table in a later lecture. So 2 and 3 make great representative periods. 4 and farther down have extra elements in them that aren't going to show you the trends as well. So if you're looking for examples, stick to periods 2 and 3. 1's too small, 2 and 3 are just right. Groups are the vertical columns, so the ones that go up and down on your periodic table. We also call groups families. So families of elements. We are also going to see trends as we go up or down a group. So they're going to ask you from top to bottom or from bottom to top. They'll ask you from left to right or right to left. Make sure you're reading the questions very carefully. So we will have more trends as we go down the groups. Again, when we're looking at trends in groups, I want you to stick to groups 1, 2, and 13 through 18. 1 and 2. 1, alkali metals. 2, alkaline earth metals. They're going to show very nice trends for what we're looking for. Group 17, the halogens, also very good group for looking at the trends. So any of these will work. Avoid group 18 for trends. Group 18 are the noble gases, and they, because that very, very stable electron configuration, a lot of times they break the trend. You don't always see the trend when you look at their data and their numbers, so I would avoid them if you're looking for an example group, but you do need to know the name. Okay, one of the things that you're going to notice about the groups, and if we look at our periodic table again, the valence electrons, remember valence electrons are the very last number in the electron configuration. As I go down group 1, it's 1. 2-1, 1 valence electron. 2-8-1, 1 valence electron. 2-8-8-1, 1 valence electron. Down group 2, they're 2. 13 is 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7. 18 is 8 with the exception of helium, so be careful of that. Group 18 actually has 2 different numbers for valence electrons, 2 for helium because he's so very, very tiny and small, 8 for all of the rest. The transition metals here in the middle, you're going to see differences. The transition metals, we'll talk about why they're different. For the most part, they all have 2 or 1 or no valence electrons. Sometimes you'll see one that just says 18 on the outside. That's because there are no valence electrons. We'll talk about the transition metals specifically different. So if they want to know the trend in valence electrons, they are again talking about groups 1, 2, and 13 through 18. Okay, atomic radius, covalent radius, going to be the same thing. If we look on reference table S, they call it atomic radius, and it's your last column over here. When they want to know any of these trends, ionization energy, electronegativities, melting points or boiling points, freezing points or condensation points, densities, atomic radius, they're all here on reference table S, so there's no reason to get these wrong. If we want to look at the trend going down a group, I would say pick group 1. So here's lithium, and here's his radius, 130. Here's sodium, and here's his radius, 160. Here's potassium, and his radius, 200. So pick at least 3 going down the group. So 130 to 160 to 120. As you go down a group, the radius gets larger. As the electrons get farther away, it gets larger. So as you go down a group, the covalent radius or atomic radius increases. Let's talk about if we go across a period. So if we're going to go across the period, I would again pick period 2 or 3. So if I stick with period 2, here's lithium, beryllium, boron, carbon, nitrogen, oxygen, and I would stop at fluorine because the noble gases again, sometimes break the trends because they have that stable electron configuration. But as we go across the period, we're going from 130, 99, 84, 75. It's getting smaller. So they get smaller as you go from left to right because there are more protons in the nucleus. And remember, the protons are pulling on those electrons. And they're not going to pull just on the total electron. Each individual electron gets tugged on by this nucleus. So you start off with 3 protons pulling on the outermost electron, and then you switch to 4 protons pulling on it, and 5. It's going to tug it in a little bit tighter, and so the radius gets smaller. So you can look up the covalent radius right on table S. Here it is graphed out for you. This is one of the things that they like you to do. Maybe look up the data on table S and then graph it and then describe the trend. So on this graph, they've used different colors, and the colors match their periodic table over here. But here's period 1. There's hydrogen and helium. Here's period 2. Here's period 3. Here's period 4. Now you'll notice where it gets a little weird in the middle. Those are your transition elements. These are those 2 bars that are down at the bottom. That's the first row in the bottom, so they've skipped it. Here's your transition elements. But again, the general trend is that it decreases. So across the period, radius decreases. So from left to right, decreases because there's more protons. And down a group, it increases, so we're going down, it increases, and that's because there are more principal energy levels. Okay, so memorize those 2 things. When we talk about ionic radius is not on table S. This is something you have to memorize. It's not going to be on your reference tables at all. When we make positive ions, remember that we are removing electrons. So if we just took lithium for an example, so I have my nucleus, I have my first principal energy level, I have my second principal energy level, and I have his 1 valence electron out here. When he becomes a +1 ion, we lose 1 electron. So if I lose 1 electron, I lose an entire principal energy level. So therefore, positive ions are smaller than the atom that they were formed from because there are fewer principal energy levels and there's fewer electrons. So now I have more positive protons pulling on fewer electrons. On the negative side, we don't change the number of principal energy levels, but we change the number of electrons. So if I'm fluorine, negative ions are formed by gaining electrons. So if I'm fluorine and I have 9 positive protons pulling on 9 electrons, when I become a fluorine -1 ion, I now have 9 positive protons pulling on 10 negative electrons, and the electrons can win and kind of move out a little bit. It distributes that pull on them, and they get slightly larger. So negative ions are larger than their atoms because there are more electrons. So you just basically have to memorize the trend and be very careful when you read the questions. Positive ions are smaller than their atoms. Negative ions are larger than their atoms. And remember that they're all gaining and losing electrons to try and look like noble gases. Metals tend to lose electrons and become positive ions. Nonmetals tend to gain electrons and become negative ions. Ionization energy is the amount of energy that it takes to remove an electron. The more electrons there are between the outermost electron and the nucleus, the easier it is to knock the electron off. They called it the shielding effect. It's kind of like if you're picking up paper clips with a magnet. If you have a long chain of paper clips, the one at the end is easier to knock off than the ones that are closest to the magnet. Same thing happens here. So the more electrons you get between you and the nucleus, the more those electrons are shielding the outermost electron from the pole of the positive nucleus. So if we try to look at this trend in ionization energies, we're going to use table S, and across a period. So again, let's use period 2. So lithium, here's first ionization energy. This is the first one because it's the first electron to pull off. You would have ionization energies for the other electrons that would be different. But look at these numbers. We go from 520 up higher and higher to 1,681. So it increases. So across the period, the ionization energy increases because there are more protons. Remember, they're in the same principal energy level, these electrons. So even though there's more electrons, they're all starting the same distance away from the nucleus. So more protons in the nucleus help to pull them. Let's look at the trend down a group. So if we're going to go down a group, let's try the lithium, sodium, potassium again. So here's lithium's ionization energy. Let me switch to a different color. Lithium, 520. Sodium, 496. Potassium, 419. It's decreasing as we go down a group. So as you go down a group, the ionization energy decreases because there are more electrons. They're farther away because there's more principal energy levels. And we call it the shielding effect. That's what's taking place there. So memorize the trend. Across a period, it increases because there's more protons. Down a group, it decreases because the electrons are farther away. There's more principal energy levels, and there's more shielding. And remember that you can go to table S to look up the numbers specifically. And that's it for Lecture A.